We are now looking at the teaching video on partial fractions. So point 1, an algebraic fraction is the ratio of two polynomials of the form px over dx, where px is a polynomial dividend. So I have polynomial dividend, and for D it would be a divisor in X. If the degree of Px is less than the degree of dx, then this algebraic fraction is a proper fraction. However, if the Px is more than or equal to the degree of dx, then this algebraic fraction is an improper fraction. So a few things to note, and we'll be using this representation throughout this video. So Px is the polynomial dividend and the dx is the divisor in X. So what it means is that this expression is in terms of X and that expression is also in terms of X. For point 4, an improper fraction can be changed to, and I put it this way, Qx plus Rx over dx. So Qx is a quotient polynomial and Rx is a remainder polynomial, and this is a proper fraction. So point 5, the process to convert this algebraic fraction to Qx, the quotient, plus the remainder divided by the divisor is called long division. Point 6, there are 3 basic types of denominators for algebraic fractions. They are what we call the linear factor, also the repeated linear factor, and lastly the quadratic unfactorizable factor, or quadratic factor that cannot be factorized. Let's look at point 7 now. So the first type that we're looking at, if you're looking at the denominator of the algebraic fraction, we have linear factors. So the first type is linear vector. And type 2, if you just observe this, that is a repeated linear vector. So the emphasis is repeated linear vector. And just to highlight, these two are actually linear vector. This one is a repeated linear vector. This one, of course, is just a linear vector. For type 3, the focus is on this. That is a quadratic expression that cannot be factorized. So, unfactorizable quadratic vector. So the expression that I need to use in order to split up this fraction into more than one partial fractions, I would use a constant over the linear vector and another constant over the next linear vector. As for this one, I'll begin with the linear vector first. A over ax plus b, followed by b over this vector cx plus d. But I have the third constant over cx plus d squared. So for the third one, I'm dealing with a linear vector, also a quadratic unfactorizable vector. So the first one, for the linear vector, a over ax plus b. Then for this quadratic vector, I have bx plus c over cx squared plus d. So the form that we can use to split up this algebraic fraction for the linear vectors will be just a constant over the linear vector. For repeated linear vector, to split up this fraction, I will have to make use of a constant over the linear vector cx plus d, then the second constant c, over the linear vector squared. That is for repeated linear vector. And the third one, to split this up, more importantly for the unfactorizable quadratic vector, I would have a linear expression on top over the quadratic unfactorizable vector. Let's look at point 8. An algebraic fraction is equated to a suitable expression to work out the unknown numerators. These are the three methods. So the method will be, one is the use of suitable or special So use of substitution of special values of x, that is one. The other is the use of selective comparison of like terms. Of course, there is another part to this, to do comparison of terms where the expression is fully expanded. Then the use of cover up method. So these are the three methods we'll be using. One, substitution of special values of x, and the other one, selective comparison of like terms, and the third one, cover-up method. For these first two, it is a familiar item in the polynomial section of work. We encounter that in comparison of terms. Now we look at point 9. There are two ways to set up the comparison of coefficient of like terms on the left-hand side and the right-hand side. So the first way is just using selective comparison of like terms. Next, of course, we are looking at full expansion of terms for comparison. So the expression on the right-hand side particularly are expanded fully so that term by term, the left-hand side, perhaps the x squared term will be compared to the x squared term on the right-hand side, and also the x term on the left-hand side compared to the x term on the right-hand side. So selective, so we don't need to expand fully the right-hand side expression. The full expansion, the expression must be expanded fully. Point 9, given this, where we have an algebraic fraction split up into its partial fractions, using the cover-up rules, this is what the steps are. To work out A is just the constant for the numerator of this algebraic fraction. So taking that factor, ax plus b equated to a 0, I will get ax equals to negative b. X is just negative b on a. So I would then take this value and put it into here. And you notice that over here, the denominator expression is actually the expression of the other linear factor, cx plus d. So for b value to be worked out in this cover-up rule, then I will have to take this factor, cx plus d, equated to a 0. So Cx is equals to negative d. X is just negative d on C. Now that value of x will be put into this form. And you notice that for the value of b to be worked out, I will have the linear polynomial, which is over here, with the value of x put in, divided by the expression of the linear factor belonging to the first algebraic fraction. So this is a foolproof way of working out the value of a and b quickly. So this is just another method to add on to your repertoire of problem solving skills. Now for 11, we need to change this to this form. So if I expand the denominator expression, and I will have a cubic expression. This cubic expression is of the same degree as the expression of the numerator. So in this case, that is considered an improper fraction. And we need to actually convert this form to this form using long division. So the way to do it is, when this is fully expanded, I have 2x cubed plus x. Here I have 2x cubed. Now this is what I'll do before writing in the constant. So I need to multiply this by a 1. And I'll get 2x cubed plus x over. Now if I just take the top expression minus the bottom expression, I have got negative x. This is where I put in the 3 plus 3, transfer it down here. So this is my quotient, this is my remainder, and this is my divisor. So that is my polynomial expression for the dividend. So put all that together, I have 2x cubed plus 3 is equals to 1 times the divisor plus the remainder. But I want quotient here, so the dividend must be divided by the divisor, so that I have 1 plus 3 minus x over the divisor. And that can be split up to what I had at the beginning, which is just x bracket 2x squared plus 1. So you can see this is a linear factor and this is the quadratic unfactorizable factor. So to get to this form, we need a long division, And we need also to be very familiar with this statement. Dividend is equals to quotient times the divisor plus the remainder. Another way to put it, when I divide throughout by the divisor, I have the dividend divided by the divisor equals to quotient plus the remainder divided by the divisor. For point 12, it's just an exercise to state the suitable expression of the partial fractions for this particular algebraic fraction. The first thing to do is to recognize the type of factors in the denominator. This is the linear factor, this is the quadratic unfactorizable factor. So we have 7x minus 12 over x plus 2. Then I have 3x squared plus 1. For the linear factor, I will have a constant a over that factor plus, this is a quadratic unfactorizable factor. It's quadratic, so the numerator ought to be a linear expression. So that is the suitable form that we can have. But in order to solve it, then I will have to make the denominator the same and make sure that the numerator is compared to the numerator on the left-hand side of the expression. So for this segment of the video, we have touched on the three basic types of factors for denominator and the ways in which we will actually solve for the unknown. Basically, the unknowns in the numerator of the algebraic partial fractions. So we have come to an end of this video.